All right. So, okay. Okay, so I'll show that composition of two reflections is a rotation. Okay, so let me form the setup. Suppose this is our coordinate system R2, and we take reflections with respect to two lines, let's say L1 and L2. Let's choose a vector here, V1, and a vector here, V2. And then to write the reflection with respect to, for example, this line L1, I need, so what does reflection does? Reflection keeps this vector the same, but it sends the orthogonal map, orthogonal vector to this one, to its inverse, right? Reflection takes, and if you take this vector, let's say U1, which is orthogonal to U1, it will send it to minus V1. So reflection with respect to the line L1 maps V1 to V1. So I can write this thing as a pencil like this. This will, when you feed V1 to this, it will eat and give you 1, and then you will get V1. And if you feed U1 to this, it will give you minus U1, right? And this one, of course, when this guy eats U1, it will give you 0, right? So this is reflection with respect to the line L1. And L2 is this gadget. Well, maybe I should draw L2 in a different color. Let's say L2 is this line. Take V2. And this is L2. And here, of course, we will need also a vector perpendicular to L2, and it is, let's say, U2, right? And what is reflection with respect to L2? That will just map V2 to V2 and U2 to minus U2, so U2 star. Okay. Here, of course, we got, beta 1, U1, no, U1 or V1 U1, and beta 2, V2, U2. These are bases for R2, and I am using also the new bases like V1 star, and V2 star, basis for build of R2, right? R2 star. So this notation suggests this, and we know that, for example, U1 star at U1 is 1, but U1 star at V1 is 0, and so on. Right? Since they are dual elements. Okay, now my claim is the following. My claim is this. Composition of these two, so R L2, R L1. If I first apply reflection with respect to L1 and then reflection with respect to L2, this is the rotation. Let me write it like this, rotation. How much rotation? Rotation is about, okay, 2 things. Counterclockwise rotation. 2 theta radian rotation. About those. What is theta? Theta is the same. Okay, theta is the same. So my claim is that the composition of these two reflections is rotation of the plane. How many radians? 2 theta radians. So twice the same. Okay, that's my claim. Well, let's see how we can prove this. Okay. The thing is the following, the important fact is the following. Okay, now let me write. Okay, V1, U1 like this, and I have this 2 vectors. What they are? So I have V2 and then U2. And how much this angle is? This is theta, right? The angle between the 2 lines is theta. Now, what I will do, first I will write U2 and V2 in terms of U1 and V1. So this is like, the XY plane, a little bit rotated. You can just rotate like this and regard this as X and this guy as Y. Then what would be this vector? Well, V2 is nothing but, right? Let me write here. V2 is just, I can regard all of these as unit vectors, let's say, unit vectors, same length. So this is just cosine theta U1 plus sine theta U1. What about U2? Well, I have to consider now this angle. This is just theta plus 90 degrees. So this is cosine theta plus pi over 2 U1 plus sine theta plus pi over 2 U1. What is this? Cosine theta plus 90 pi over 2. Sinüs olacak ama eksilisi olacak değil mi? Kosinüsü 90 derece yani çevirirseniz kosinüs pozitif taraftan negatife gelecek. Sinüs olacak. Minus sin theta U1 and this will be cosine theta U1. Okay, so U2 is this. What about the dual vectors? Like, I want to write this thing in terms of U1, V1, and U1 star, V1 star. I already wrote V2 and U2 in terms of V1 and U1, but I have to write also the dual vectors in terms of the dual. What will be the duals? Can you guess what will be the METU star? B2 bu. Bunun duali ne olur sizce? Kafadan atın. Efendim? The same coefficient, right? So your guess is this. Cosine theta V1 star plus sine theta V1 star. This is our guess. What about V2 star? Well, I did this once. I can do it infinitely many times, right? So theta 1 V1 star plus cosine theta V1 star. Peki doğru mu? We have to check, right? How can you check? Well, if these are the dual, then this guy should evaluate 0 on V2, 1 on U2. And this guy should evaluate 1 on V2 and 0 on U2. So let's check it. V2 star, V2. Okay, now cosine theta V1 star plus sine theta V. Pardon? V2 bu. Bu V2 star bu, özür dilerim. V2 star will eat V2. What is V2? Cosine theta V1 sine theta U1. Bunu doğru mu yapıyoruz? Yani bu vektörün θ kadar döndürülmesi bu değil mi? Evet. Yani acaba bir yerde bir eksi mi vardı diye düşündüm ama. Tamam. Şimdi bunu yesin. Nasıl yiyecek? V1 star V1'ı yiyecek 1. Bunu yiyince 0. Katsayıları çarpıyorum. Cosine square theta plus sine square sine when this guy eats this guy and gives us 0, but this guy eats this guy and gives us 1, and the coefficients just sine square theta, that is 1. What about V2 star evaluated on V2? Well, cosine V1 star plus sine theta U1 star, and then I'll write U2. What is U2? U2 is minus sine theta V1 plus cosine theta U1. So what is the result? This guy eats, this guy gives us 1. What are the coefficients? Minus cos theta sine theta. Plus this guy eats, this guy gives us 0. When it eats, this guy gives us 1. What are the coefficients? Sine theta, cos theta, equal to 0. Okay? So these are the right basis elements. Tamam mı? Yani attık tuttu. Tutmasaydı ne yapacaktınız? Yine atacaktınız, evet. Research budur. Ama tabii ki her seferinde hatanızdan ders alacaksınız. Yani aynı şeyi yazmayacaksınız mesela. Değil mi? O zaten çalışmamış. Başka bir şey. Ders aldığınız sürece hata yapmakta sıkıntı yok. Bu türlü sonsuza kadar insan deneyebilir. Onda da bence sıkıntı yok da. Okay. O zaman so we wrote U2, V2, V2 star, U2 star in terms of the V1, U1, and so on. So ours L2 can be written like this. It was, let me write, V2, V2 star minus U2, U2 star. So what is V2? I want to write everything in terms of U1, V1. Cosine. So this is just cosine V1 plus sine cosine theta, of course, V1 plus sine theta U1. Tensor V2 star. V2 star is cosine theta V1 star plus sine theta U1 star. So what is this then? Oh, this is one term, of course. I have two terms, U2. What is U2? U2 is plus, no, this is minus. I'm sorry, there's minus sign here. And then I have U2. U2 is minus sine theta V1 plus cosine theta U1. And then here I have cancel U2 star minus theta sine theta V1 star plus cosine theta U1 star. So let's write this down. Şimdi evet. Şunda şu var. Bir kere buradan ne gelecek? Kosinüs kare cosine square theta V1 star. And then cos and sine cos theta sine theta V1 U1 star. Right? I multiply this guy with this one and this guy with this one. Now, what about the other terms? This guy and this guy, so sine theta, cos theta, U1 cancel U1 star plus sine squared theta, U1, okay, U1 star. Bitti mi? Bitmedi. Bir de bu var. Okey. Ama burada belki biraz kestirmeye kaçabiliriz. Evet. Şimdi bakın dikkat ederseniz buradan ne gelecek? Eksi sinüs kare theta V1 star. Burada kosinüs kare vardı. Eksi sinüs kare geldi. Yani şu katsayı kosinüs kare eksi sinüs kare oldu. Cosine square theta minus sine square theta. Cos 2 alfa yazarız. Tabii ki. Cos 2 theta. Belki cari olur. Cos 2 theta. Tamam. Bunun katsayısı V1 U1 star. So V1 U1 star. It is minus plus. So the same thing one more time. So I have 2. And 2 times this is sine 2 theta. So you see, trigonometry is important. And then what else? I have U1 V1 star. U1 V1 star. So burada yazacağım. U1 V1 star eksi değil mi? Minus U1 V1 star. Bu da artı. O zaman 0 oldu. Ha, 1, 2, 3 tane var. Pardon. Ne yapıyordum ben?
U1, V1 divided.
U1, V1. Bir eksi burada var, bir eksi burada var. 2 tane var. Bu 2 oldu. Sinüs 2 teta. U1, kosinüs kare. Ama minus oldu sanki. Ha, o da kosinüs minus sine squared minus cosine squared. So it is minus cosine 2 theta. Minus cosine 2 theta. Tamam mı? İtirazı olan var mı? Any objections? Just high school trigonometry, right? Okay. Last step. So, RL2 composition RL1. RL2 is what? Let me write down RL2. So it is just cos 2 theta V1 tensor V1 star plus sine 2 theta V1 star plus sine 2 theta U1 V1 star and minus cosine 2 theta U1 star. U1 star. Okay. Composition RL1, that was easy. RL1 is over there. V1 star minus U1 star. Okay, now what is the result? Okay, now this guy will eat this guy. You will compose this two. What was the composition? Kim kimi yiyorsa yiyecek, değil mi? Burada bunun yanına yazarsanız bu nesne bunu yiyecek. Efendim? Evet, bunu yiyince de 1 verecek. Ne kalacak geride? V1 star kosinüs 2 theta. Kosinüs 2 theta V1 star. Peki. Sonra bunu yiyecek. V1 star U1'i ben V1 star eats U1, it gives you 0. So nothing comes from this one. What about this guy? V1 star eats this guy, gives us 0. Like U1 star eats this guy and gives us 0. U1 star eats this guy and gives us 1. And then what is the result? V1 tensor U1 star, and the coefficient is minus 2 sine theta. Ne dedik? Bu gitti V1 tensor U1 star. Okay. What about this? V1 star bunun ince 1 verecek. Nedir? Sinüs 2 theta. Sinüs 2 theta. U1 V1 tensor. U1 tensor V1 star. U1 tensor V1 star. And then this guy U1 star eats this guy, gives us 0. Eats this guy, gives us 1. Minus so plus cosine 2 theta. Ne çıktı? U1 star 17, 1 verdi. U1 star. Peki, o zaman bu ne oldu? Now, what was our claim? Claim was this is rotation about the origin 2 pi radian. So let's see if it is really the rotation. Okay. So RL2 composition. Şöyle bakalım önce. First, let's look at this. So if I rotate 2 theta radian, so this is let's say V1, and this is U1. If I rotate this 2 pi radian, not 2 theta radian, I will get this vector, let's say V3. So this is 2 theta, and this will give me so U3, and this is 2 theta, right? Yani 2 theta döndürmek V1'i V3'e, U1'i de U3'e götürür. Peki bu U1, V1 ve V3 nedir? So what is V3? It is just cosine 2 theta V1 plus sine 2 theta V2, right? No, not V2, U1. And what about U3? 90 derece ekliyoruz. 90 ekleyince eksi sinüs. Değil mi? U1 artı kosinüs 2 theta U1. O halde so 2 theta radian maps U1 and V1 to these two vectors. So let's see. Yani şunu biliyoruz. Rotation 2 pi rotate 2 theta rotation sends V1 to V3 and rotation about origin to theta radian maps U1 to U3. And I claim that composition is the rotation. So let's see. RL2 composition, RL1 applied to V1. So when I feed this guy with V1, let's see what we get. Buna V1 yedirirsem ne elde ederim? 1. Buna V1 yedirirsem 0. Buna V1 yedirirsem 1. Buna yedirirsem 0. O halde V1 yedirdiğimde buna 1 elde ettim. Kosinüs 2 theta V1. So this is cosine 2 theta U1. Buradan da ne çıktı? V1'i yedirince sinüs 2 theta U1. Bu da nedir? E3. U1 nedir? When I feed U1, so when I feed U1 to this guy, it will give me 0. This one will give me 1. So minus sine 2 theta V1. And this one will give 0, and this will give us cosine 2 theta. So I will get minus sine 2 theta V1 plus cosine 2 theta u1. What is this vector? It is just u3. So what we see is that this linear map, this is the linear map, and this linear map sends the basis elements v1 and v2 to the same elements, right? The image of this one is v3, the image of v1 is 3, and image of this guy on the second basis element is u3, and the image of this linear map on the second basis element is again u3. So these two linear maps agree on a basis. Therefore, they are the same. Okay, and so since this is the basis, this rotation is equal to R L2 R L1. This is a nice exercise on tensors, right? Tensor products and about many other things we have considered so far. Yeah.
Could you explain how to find the equal tensor products of R and 1?
Okay. Well, this is reflection with respect to the line L1. If it is reflection with respect to the line L1, it will keep L1 fixed, right? It won't move L1. So it will send V1 to V1. What is the tensor which maps V1 to V1? It is this one. When you feed this guy with V1, it gives you 1 times V1, so it is V1. And it should map the perpendicular vector U1 to minus U1. So this guy, right, just sends U1 to minus U1. And this guy will give us 0 on U1, and this guy will give us 0 on V1, so they don't interact. So this is the right thing. Bu nesne. So this maps V1 to V1, U1 to minus U1. So it is the reflection. The same.
Is there any way to write R1 just with this one tensor product?
No, we will do that because it has rank 2, that linear map. And if it is rank 2, then the minimum number of tensors you need to use to write this as a tensor product is 2. So that's a minimal representation. Reflection isomorphism. Isomorphism ise basis'i basis'e götürür. Yani imajı da 2 boyutlu. Onu yapacağız. Onların üstünden geçeceğim. Başka sorusu olan var mı? Yani işlemler kafa karıştırıcı olabilir ama hani teorik olarak bir zorluk yok. Sadece sabredeceksiniz, sonuna kadar doğru şekilde yazacaksınız her şeyi açık çıkıyor. Tamam mı? Ben de bu hesabı hayatımda ilk defa yaptım. Yani bunu itiraf edeyim. Ama 2 reflection and rotation olduğunu başka şekillerde de görebilirsiniz. Doğrudan geometriyle de yapabilirsiniz. Hani high school geometriyle de. O da güzel bir egzersiz ama tensörlerle de yapabiliyoruz. Matrislerle yapmayı deneyebilirsiniz. You may try to do this using matrices. You will get similar computations. You will have 2 matrices. You will multiply them. And you will get a third matrix, and third matrix will be the rotation matrix. You can do it that way also. Okay. All right. Şimdi So last time we were evet, teoremi vermiştim, ispat etmedik değil mi? Şimdi ben teoremi bulayım. Sorusu olan var mı başka? Onunla ilgili yok. Siz görün. If you don't understand this good enough, I mean, if you feel that you don't understand, then just try to do it by yourself, okay? You will learn. I mean, if you try by yourself, you will learn all the details. Dediğim gibi hani başkasını seyretmek güzel ama o öğretici değildir. Yani sadece size güvenini verir. Yani bu adam yapıyorsa ben de yaparım. Bu önemli bir şey. Birinin yaptığını görmek. Ama yapmak başka bir şey. Okay, so last time we wrote this theorem, but we didn't prove. What was the rank? Rank was the dimension of the image, right? Maybe I should start with the definition. If we have a linear map, suppose this is a linear map. What was rank of A? Rank of A head is defined to be the dimension of image A head. Image A head is a subspace of W, and the dimension of this subspace is called the rank of A. A'nın görüntüsünün imajı. Görüntü sıfırsa boyutu sıfır olacak. Evet. And the theorem was this theorem. The rank of a head is the smallest number of terms necessary to write an operator the operator olması lazım. The operator. Zaten olduğunu söyleyeyim. The operator a head is a sum of single term tensor products. In other words, the operator a head can be expressed as like this, a head came from 1 up to rank of a head. Some vectors and some productors in where W tensor is psi. Yani bu operatörü bu şekilde yazabiliyorum demek. rank A tane terimde. Tamam mı? Burada bitmiyor tabii. Böyle yazabilirim, but not as a sum of pivot terms. Yani 3 tane terim şeklinde yazabiliyorum ama 2 taneyle yazamıyorsam o zaman onun rankı 3. Tamam mı? Bu da ne demek? Görüntü kümesinin dimension'ı 3. Okay, now let's see how we can do this. Okay. All right, so we have this linear map. Then we know that kernel of A hat, kernel of A hat is a subspace of D, is a subspace of D. And suppose this has dimension n and dimension n. Okay, let's write like this. So this is n-dimensional and this is m-dimensional. They are vector spaces over the same field. Okay. And I know that kernel A is a subspace of D. Assume that it has dimension k. Yani bu subspace'in dimension'ı k olsun. Okay. Then okay, B1, Bk be a basis for this kernel. Madem k boyutlu, right? I assume that it has dimension k, so it is a basis consisting of k elements. All these vectors, of course, are in D. But we know the following: whenever I have a linearly independent set, so this is a basis for this subspace, in particular, it is linearly independent. So this is linearly independent in this vector space. Then I can extend this to a basis of D, right? Each time I put a vector, which is not in the span of this one, so I just get bigger and bigger linearly independent sets. This will, and when I reach n, right? I will stop there. So let beta V1, Vk, Vk plus 1. How many vectors should I add? Well, k n minus k vectors, right? Here this is for B obtained from the linearly independent set obtained containing the linearly independent containing the linearly independent set V1, V2. We discussed this, right? You can always extend a linearly independent set to a basis of your vector space. You just put vectors which are not in the span. Yes.
How do we know the dimension of kernel is less than the dimension of D?
Okay.
And do we know that the kernel is not and it's not
Kernel contains zero vector.
is it a linear map?
What?
A delta tilde is the linear map.
Yeah, sure, of course. This is linear algebra. So everything is linear. Okay. Yeah. It's a linear map. Otherwise, I cannot say anything. Şimdi tamam mı?
No, the first question.
We proved that when you have a linearly independent set, you can extend it to a basis of your vector space. So to extend it, you have to add some vectors. We proved that. So it necessarily has fewer dimensions. Tabii ki az. Eşit olursa o subspace her kendisine eşit.
Elimizdeki ve kernel aynısı.
Olabilir.
Ekleyemiyoruz.
0 tane eklersin. Biz ne dedik? K minus n tane ekliyoruz dedik. Ben K minus n 0 değildir demedim ki. Tamam mı? Sorusu olan? Okey. Bir de şunu biliyoruz. We also know that image of a head is a subspace of Wn, right? Okay, now our claim is this. The dimension of W is M. Dimension of W is K minus n. The dimension of W. Ya da hatta şöyle diyeyim. The dimension of W değil. Is n minus K. And actually şu küme. So this vectors you edit extra to obtain a basis for V, their images. So A text V K plus 1 up to A head V and is a basis for image A head. Okay. So this has dimension n minus K, and I can tell you what's the basis for this. Basis for the image are just the images of this extra vectors. These ones already goes to 0, right? So this first K guys goes to 0. They cannot contribute to a basis. Bunlar yani W içinde zaten öldüler. Basis olacak vektörler bunların dışında olması lazım. Tam öyle işte şu vektörler görüntünün bazını verir. Bunlar ölecekler. Evet.
Bir base yani kernel mühendis substation'dan eminim. Ona base olması gerekiyor.
Yani şöyle D'yi şimdi D'nin I want to know what is the image of this guy. The image of this guy cannot be bigger than this one, but it is probably smaller. Why is it? Because some of the vectors here goes to 0, so they die out. So I just, ignore them, and this is how I do it. These are the first K values; they go to 0, and the rest will survive, and they will form a basis for the image. Okay. Yani ölecekleri ayırıyorum. Geri kalanları orada hani yaşayacaklar. Onlar işte imajı gelecekler. Ona değişecek. O yüzden hani ölecek olanları ayırmamız lazım. Tamam mı? Okay, let's stop and I'll continue in the second hour.